What is bandwidth and latency in your system? At the first look, you may say they're both the same, right? Because we are talking about the speed of the system. They may sound the same thing, but they're totally different beasts. And if you don't understand them separately, you may end up optimizing the wrong thing in your program. So, hello everyone. Welcome back to the what every programmer should know about the memory. In the last few videos, we were talking about different concepts, cache hierarchies, NUMA, and how memory access patterns affect the performance of your program. But there are two terms that keep coming up, and they're often misunderstood: bandwidth and latency. In this video, we'll talk about what actually bandwidth is and what actually latency is, and how they can affect the performance in very different ways, and how to measure and tune for each one. Let's start with latency. Latency is a delay between requesting a data and receiving it. It's measured in nanoseconds. Think of it like this. Latency is how long your system will respond a single memory question. You ask, for example, "Hey RAM, what is already stored in this address?" And the latency is the time until the RAM answers you back. In real systems, latency is often between 80 to 120 nanoseconds for DRAM. But let me put that in perspective. If your CPU is as fast as the race car with the speed of light, then 100 nanoseconds is like waiting for 8 seconds to get answer back from RAM. That's very long. That means every single memory access that misses the cache has to pay that latency penalty, and that can add up fast. So if your code has a lot of random, unpredictable memory accesses, like following a pointer in a tree or chasing linked list nodes, you are latency bound. Now let's talk about bandwidth. Bandwidth is amount of data that you can transfer per second. It's measured like gigabyte per second. Imagine latency is the time to fetch a single byte of data. Bandwidth is how many total bytes you can stream per second. Think of it like a width of highway. The wider the highway, the more data cars can go through this highway at once. For example, DDR4 memories might have the bandwidth of 25 to 30 gigabytes per second per channel. High-end servers, they can exceed 100 gigabytes per second with multiple channels and multiple sockets. Now here is the key. If your code streams large data arrays, processes image buffers, something like this, you are probably bandwidth bound, not latency bound. You are moving huge volume of data, and your performance depends on how fast RAM can move these gigabytes of data into your desired location, not just how fast the RAM can answer to the single query. So latency is response time and bandwidth is transfer capacity. They're totally different terms. Let me give you a real-world example that can simplify the difference between these two terms. Imagine you're ordering a pizza delivery. You place the order. It takes them 30 minutes to bring you one pizza to you. That is their latency. But now what if they bring 10 pizzas at once stacked in the delivery car? That's the bandwidth. So if you're ordering a single pizza, latency matters. But if you're ordering 10 pizzas, bandwidth matters. The same applies to the programs. If you access lots of small objects, pointer by pointer, you're like a single pizza customer and you care only about the latency. But if you are crunching through the large data or a giant streaming files, you are basically throwing a data party, and bandwidth is king here. So how do you know if your program is latency bound or bandwidth bound? Let's start with perf. On Linux, you can measure cache misses and memory reads using hardware counters. Try this, for example. This gives you an idea how often you miss cache. High miss rates suggest that you are suffering from the latency cost. Now to measure the bandwidth, we can use the tool like MBW, which is the short form of memory bandwidth. This shows how fast your memory subsystem can copy or write large blocks. You can also measure actual program bandwidth using customized benchmarks, which streams and time how long it takes for them to be finished. Another way is profiling with Valgrind's cache grind or use Intel vTune, which gives you the incredibly detailed information about memory stalls, bandwidth utilizations, or even NUMA-related slowdowns. Ultimately, it comes down to your access pattern. Random means latency cost, Streaming means bandwidth cost, unalignment and fragmented means the cost from both bandwidth and latency. Now the big question, what can you do about it? So in case that you're latency bound, you can keep your data as close as possible to the CPU. You may prefer stack over heap or cache-friendly data structures. You need to also avoid pointer chasing. You can flatten data structures if possible or use arrays instead of linked lists. If your programming language or your compiler allows it, you can use prefetching hints as well. In the case of facing the bandwidth bound, you need to align your data. 64 bytes alignment, for example, reduces false sharing and it can also help memory buses. You need to also avoid redundant reads and writes and make the cache reuse your friend. Use SIMD operations where it is possible to process multiple elements in one instruction. Try to process in blocks as well, also known as tiling or blocking, to work with small chunks that can fit into the cache. And sometimes your code is bounded by both. For example, if you're loading huge amounts of data and doing pointer heavy access, that's when you really need to consider your algorithm or data layout. If you want to recap, so latency is about how quickly you can access a single byte from the memory. Bandwidth is about how many bytes you can transfer per second. And your performance depends on which one of these two parameters is the bottleneck. And profiling tells you exactly where you are losing cycles. So don't confuse bandwidth and latency. They might both affect your performance, but they do it in different ways. And if you are not sure which one is hurting you, profile, measure, optimize, and repeat this cycle again. Okay, that's it for today. If you are interested in such topics, don't forget to hit a like and comment down below. And if you don't want to miss the next videos, don't forget to subscribe and ring the bell. Until the next episode, good morning, good afternoon, and good evening. Bye.